Hello everyone. This week we are going to discuss the graph structure, and this is going to be the last week of our course materials, and the week 14 will be the additional course material like the simulation week, which are not going to be covered in the final exam, but it's just an information that I want to give you. Okay, so actually week 13 is our last course material. Sorry. So our weekly objectives are this. This week we are going to study graphs, and these graphs, to study graphs, as usual, our objectives are understanding its structure and its operations. Okay. So how it is structured and how it operates, and particularly some of the operations are kind of difficult, so we need a special algorithm to do that, and we are going to study that algorithms. Okay, so these are what we are going to learn. So first thing is first, we have to understand what the graphs are, so we need to define it. Graphs are kind of ordered collections, but we have been dealing with the different types of the ordered collections already. First thing was the list. Okay, and however, this list was not kind of ordered; it's unordered list. There was no single rule that can decide what would be the predecessor and what would be the next successor. Okay. However, the tree structure, there were set of rules, so that was an ordered collections. Okay. So, for example, binary search tree, left-hand side and right-hand side, and parent. There was obvious rules between those three. And the graph structures is again some kind of unordered collections. It has multiple predecessors and multiple successors. In the list, things were organized in this way: 1, 2, 3. However, binary search tree, now we have multiple successors, so one predecessor and one successors. Here we had two successors, okay, and then one predecessors. Okay. However, in the graph structures, for example, which look like this, in this case we have multiple predecessors and multiple successors. So these graph structures are not like tree, but like this one. Okay. So graph structure can be defined like this. Graph structure is a collection of V and E, and V has a multiple elements of Bi, and it's a finite non-empty set of the vertices or nodes. So these circles represents the nodes, as you can expect, and this is often called also vertices. So this is the plural form, and the single term is vertex. Okay, and the edge is also a finite set of the edges, and also is being called arcs, and also is being called rings. What we are referring to is this one, this line. This line is often called edges, or the arcs, or rings. These are all different names, but referring to the same element. Here, the edge EI connects actually two vertices in V, which means that EI somehow has information of two nodes. Okay. So EI should be a collection of two nodes, and the set of the EI, small EI, set of the small BI are V and E, and these together creates the graph. We have different types of the graph structures. First thing is the unlabeled graph structure, and the next thing is the labeled vertices graph, and labeled vertices and the weighted graph. So we are going to learn more terminology about this. So graph terminology are kind of many. So can you recall that we have learned the terminology on trees? I expect that you recall there were different types of the terminologies on trees, right? The heights, depths, and parents and siblings and the children, right? And we are going to learn the similar terminologies in this slide set. In the graph terminology, the adjacent, neighbor, and incidence, these three things refer to the same thing, which are if the 1 and 4 are linked together and 1 and 2 are linked together, these are adjacent nodes, and the neighbor nodes and incident nodes. So if two vertices are linked together, these are neighbors, and the incident nodes, adjacent nodes. And the paths between A and B are a sequence. Here it's not just a set, a sequence of edges connecting A and B. So for example, if I want to find a path from 2 to 4, we need EI of 2,1 and 1,4, right? We need these two two edges, and it shouldn't be a so simple set. It should be a sequence. It means that it's a vector. There is an order, right? So this is the path between 2, 4. Okay. And the connected graph means the path from each to every other vertices. For example, this connected graph shows that there is a path from 1 to 4, path from 1 to 2, path from 1 to 3, like this. And similarly, there is a path from 4 to 1, 4 to 2, and 4 to 3, right? Similarly, we have the passes from 2 to every other nodes and 3 to every other nodes. In this case, it's being called a connected graph. And a connected component is a graph subset. It's a graph subset containing this set of vertices literally from a vertex and their edges. So this means what? This means like this case. Actually, this is a connected. Here, this one whole set is a graph, and also here, this one set is a graph. However, this graph is not being connected graph because that there is no link between D to C. There is no way possible from D to C. So it means that this is not a connected graph. However, it does have a connected component. What's the connected component? For example, from A to C, from A to B, we can reach through the vertices and edges. Okay. It means that this is a connected component. E to D, same thing. This is another connected component. So component is actually a subset of the graph. And connected component has the same definition of connected graph, but being a subset of that graph. And finally, the complete graph, as per every pair of the vertices. So it means that we have edge for every pair of the vertices. Every vertices are being neighbors. So for example, we have 1, 2, 3, 4. It's a complete graph because then we have every possible edges, right? This 1, 2, 3, 4, 5, 6. 6 edges cover every possible rings. Okay? There is no other way to put additional rings to this graph. So it's complete graph. Here, there is one thing. Dense graph are the graphs close to complete graph. So it means that we have many edges. This sparse graph, apart from the complete graph, and actually it contains a less number of edges. So these are the distinctions. So next terminology is cycle. A cycle is a path starting from a node ending the node itself. For example, let's look at this case. Node B starts the path, and the path comes here, and goes like that. It's perfectly correct path, but it starts from the B and it ends at B. It means that there is a cycle in this edge, like this. So this is cyclic path, and there is a cycle. So this is undirected graph, right? So directed edge means that there is a direction of the flow, source and destinations. Source, here the source is B and destination is D. Here the source is D and destination is C. Here the source is C and destination is B. Does this have a cycle? Actually, yes. From B to D, D to C, C to B again. Means that there is a cycle coming back to B. So this is a cyclic directed graph. So we call it cyclic digraph. Okay. So digraph means it's directed graph. It's graph with directed edges. Every edges have direction. And another thing is that directed acyclic graph. A cyclic means that when we have A plus cyclic means that this A is empty, right? Empty. It means that it's not, right? It's not cyclic. So directed acyclic graph is a directed graph without cycle. So here this edge is being converted to have this direction. Means that to make this cycle B to D, D to C, but I cannot flow from C to B because the direction is not right. Means there is no further cycle here anymore. There is no way going back to B here, so it means that there is no cycle. No cycle. So we call it directed acyclic graph, and in short, we call it DAG. Why we have a short terminology for this particular graph structure? Because that actually is a often assumption that we use in finding shortest paths. We are going to discuss later of this week.